Hello everyone. Today we shall discuss chapter 4 Laws of Motion of class 11 Cbse board. Right? We'll today learn all these things. The first one is introduction, Aristotle's fallacy, the law of inertia, Newton's law of motion, Newton's second law of motion, Newton's third law of motion, conservation of momentum, equilibrium of a particle, common forces in mechanics, circular motion, solving problems in mechanics, summary points to ponder and exercises. First of all, let's learn line by line what is the meaning of this chapter. Laws of motion. In the preceding chapter, our concern was to describe the motion of a particle in space quantitatively. We saw that uniform motion needs the concept of velocity alone, whereas non-uniform motion requires the concept of acceleration in addition. So far, we have not asked the question as to what governs the motion of bodies. In this chapter, we turn to this basic question. Let us first guess the answer based on our common experience. To move a football at rest, someone must kick it. To throw a stone upward, one has to give it an upward push. A bridge causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without anyone rowing it. Clearly, some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop motion. You can stop a ball rolling down an inclined plane by applying a force against the direction of its motion. In these examples, the external agency of force, hands, wind, stream, etc., is in contact with the object. This is not always necessary. A stone released from the top of a building accelerates downward due to the gravitational pull of the earth. A bar magnet can attract an iron nail from a distance. This shows that the external agencies, the gravitational force and magnetic forces, can exert force on a body even from a distance. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. The external agency may or may not be in contact with the body. So far, so good. But what if a body is moving uniformly, that is, a skater moving state with constant speed on horizontal ice slab? Is an external force required to keep a body in uniform motion? Next one is what we learned about Aristotle fallacy. The question posed above appears to be simple. However, it took ages to answer it. Indeed, the correct answer to this question given by Galileo in the 17th century was the foundation of Newtonian mechanics, which signaled the birth of modern science. The Greek thinker Aristotle, 324 BC to 322 BC, held the view that if a body is moving, something external is required to keep it moving. According to this view, for example, an arrow shot from a bow keeps flying since the air behind the arrow keeps pushing it. The view was part of an elaborate framework of ideas developed by Aristotle on the motion of bodies in the universe. Most of the Aristotelian ideas on motion are now known to be wrong and did not concern us. For our purpose, the Aristotelian law of motion may be phrased thus: the external force is required to keep a body in motion. Aristotelian law of motion is flawed, as you shall see. However, it is natural view that everyone would hold from common experience. Even a small child playing with a simple, non-electric toy car on a floor knows intuitively that it needs to constantly drag the string attached to the toy car with some force to keep it going. If it releases the string, it comes to rest. This experience is common to most terrestrial motion. External forces seem to be needed to keep bodies in motion. Left to themselves, all bodies eventually come to rest. What is the flaw in Aristotle's argument? The answer is a moving toy car comes to rest because the external force of friction on the car by the floor opposes motion. To counter this force, the child has to apply an external force on the car in the direction of force. When the car is in uniform motion, there is no net external force acting on it. The force by the child cancels the force friction by the floor. The corollary is if there were no friction, the child would not be required to apply any force to keep the car, car in uniform motion. The opposing forces such as friction, solids, and viscous forces for fluids are always present in the natural world. This explains why forces of external agencies are necessary to overcome the frictional forces to keep bodies in uniform motion. But now we must understand where Aristotle went wrong. He quoted this practical experience in the form of a basic argument. To get the to get the true law of nature of forces and motion, one has to imagine a world in which uniform motion is possible with no frictional forces opposing. This is what Galileo did. First, we learn about the law of inertia. Galileo studied the motion of objects on an inclined plane. Objects 1 moving down an inclined plane accelerate, while those moving up retard. Right? Motion in a horizontal plane is an intermediate situation. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation. That is, it should have a constant velocity. An experiment by Galileo leading to the same conclusion informs a double inclined plane. A ball released from rest of one of the planes rolls down and climbs up the other. If the planes are smooth, the final height of the ball is nearly the same as the initial height, little less but never greater. In the ideal situation, when friction is absent, the final height of the ball is the same as its initial height. If the slope of the second plane is decreased and the experiment repeated, the ball will still reach the same height. But in doing so, it travels a longer distance. In the limiting case, when the slope of the second plane is zero, that is horizontal, the ball travels an infinite distance. In other words, its motion never ceases. This is, of course, an idealized situation. The law of inertia was inferred by Galileo from observations of motions of a ball on a double inclined plane, right? And what we find in practice, the ball does not come to a stop after moving a finite distance on the horizontal plane because of the opposing force of friction, which can never be totally eliminated. However, if there were no friction, the ball would continue to move with a constant velocity on the horizontal plane. Galileo thus arrived at a new insight on motion that had eluded Aristotle and those who followed him. The state of rest and the state of uniform linear motion, motion with constant velocity, are equivalent. In both cases, there is accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all time. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of three laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Every body continues to be in a state of rest or being for motion in a straight line unless compelled by some external force to act otherwise. Ideas of motion in ancient Indian science. These are the various ideas. In both cases, there is no net force acting on the body. It is incorrect to assume that a net force is needed to keep a body in uniform motion. To maintain a body in uniform motion, we need to apply an external force to encounter the frictional force so that the two forces sum up to zero net external forces. To summarize, if the net external force is zero, a body at rest continues to be at rest and a body in motion continues to move with uniform velocity. This property of the body is called inertia. Inertia means the resistance to change. The body does not change in its state of rest or uniform motion unless an external force compels to change that state. Now we'll learn about Newton's first law of motion. Galileo's simple but revolutionary ideas dethroned Aristotelian mechanics. A new mechanics had to be developed. This task was accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of three laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. Everybody continues to be in a state of rest or a uniform motion state line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both imply zero acceleration. The first law of motion can therefore be simply expressed as if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is net external force on the body. Acceleration can be non-zero if there is a net external force on the body. Two kinds of situations are encountered in the application of this law in practice. In some examples, we know that the net external force on the object is zero. In that case, we can conclude that acceleration of the object is zero. For example, if a spaceship out in interstellar space, far from all other objects with all its rockets turned off, has no net external force acting on it, its acceleration, according to the first law, must be zero. If it is in motion, it must continue to move with a uniform velocity. More often, however, we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, that is, it is either at rest or uniform linear motion, we can infer from the first law that the net external force on the object must be zero. Gravity is everywhere. For terrestrial phenomena in particular, every object experiences gravitational force due to the Earth. Also, objects in motion generally experience friction, viscous drag, etc. If then, on Earth, an object is at rest or uniform motion, it is not because there are no forces acting on it, but because the various external forces cancel out and adapt to zero net external force. Consider a book at rest on a horizontal surface. It's subject to two external forces: force of gravity, that is weight acting downward, and the net force on the book by the table, the normal reaction. R is a self-adjusting force. This is an example of kind of situation mentioned above. The forces are not quite known fully, but the state of motion is known. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of R equals that of W. This term often encountered is since W equal to R, forces cancel and therefore the book is at rest. This is incorrect reasoning. The correct statement is since the book is observed to be at rest, the net external force on it must be zero. According to the first law, this implies that the normal force must be equal and opposite to the weight W. A book at rest on the table and a car moving with uniform velocity, the net force is zero in each case. Consider the motion of a car starting from rest, picking up speed and then moving a smooth straight line with uniform speed. When the car is stationary, there is no net force acting on it. When the pickup that it accelerates, it must have due to a net external force. Note that it has to be an external force. The acceleration of the car cannot be accounted for by an internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is a frictional force that accelerates the car as a whole. We learned about friction in section 4.9. When the car moves with constant velocity, there is no net external force. The property of inertia contained in the first law is evident in many situations. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backwards with jerk. Why? Our feet are in touch with the floor. If there were no friction, we would remain where we were, while the floor of the bus would simply slip forward under our feet and the back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. If the start is not too sudden, the acceleration is moderate, the frictional force would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body, it is deformable. Therefore, it allows some relative displacement between different parts. That what this means is that while our feet go with the bus, the rest of the body remains that it is due to inertia. Relative to the bus, therefore, we are thrown backward. As soon as that happens, however, the muscular forces on the rest of the body by the feet come to play to move the body along the bus. A similar thing happens when the bus suddenly stops. Our feet stop due to the friction which does not allow relative motion between the feet and the floor of the bus, but the rest of the body continues to move forward due to inertia. We are thrown forward. The restoring muscular forces again come into play and bring the body to rest. This is an example given. So an astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the space? Assume that there are no nearby stars to exert gravitational force on him. And there are since there are no nearby stars to exert gravitational force on him and the small spaceship exert negligible gravitational attraction or the net force acting on the astronaut, acting the net force acting on the astronaut once he is out of the spaceship is zero. But the first law of motion, the acceleration of the astronaut is also zero. Now we learned about the Newton's second law of motion. That the first law refers to the simple case when the net external force on the body is zero. The second law of motion refers to the very general situation when there is no net external force acting on the body. That is, it relates to net external force to the acceleration of the body. Momentum. Momentum of a body is defined to be the product of the mass and velocity and is noted by P, it is m into v. Momentum is clearly a vector quantity. The following common experiences indicate the importance of this quantity for considering the effect of force of motion. Suppose a lightweight vehicle, say a small car, and a heavyweight vehicle, say a loaded truck, are parked on horizontal road. We all know that a much greater force is needed to push the truck than the car to bring them to the same speed in the same time. Similarly, a greater opposing force is needed to stop a heavy body than a light body in the same time if they are moving with the same speed. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone. The mass of a body is thus an important parameter that determines the effect of force on its motion. Speed is another important parameter to consider. A bullet fired from a gun can easily pierce human tissue before it stops, resulting in casualty. The same bullet fired with moderate speed will not cause much damage. Thus, for a given mass, for given mass, the greater the speed, the greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and velocity, that is, momentum, is evidently a relevant variable of motion. The greater the change in the momentum in a given time, the greater is the force that needed to be applied. A seasoned cricketer catches a cricket ball coming with great speed far more easily than a novice who can hurt his hands in the act. One reason is that the cricketer allows a longer time for his hands to stop the ball. As you have noticed, he draws his hands in the backward in the act catching the ball. The novice, on the other hand, keeps his hand fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly, and this hurts. This conclusion is clear. Force not only depends on the change in momentum, but also on how fast the change is brought about. The same change in momentum brought about in a shorter time needs a greater applied force. In short, the greater the rate of change in momentum, the greater is the force. In short, the greater the change in momentum, the greater is the force. Force not only depends on the change in momentum but also on how fast the change is brought about. A seasoned cricketer draws in his hands during catch, allowing greater time for the ball to stop and hence requires a smaller force. Observations confirm that the product of mass and velocity, the momentum, is basic the effect of force of motion. Suppose a fixed force is applied for a certain interval of time on two bodies of different masses initially at rest. The lighter body picks up a greater speed than the heavier body. However, at the end of time interval, the observations show that each body acquires the same momentum. That the same force for the same time causes the same change in momentum for different bodies. This is a crucial clue to the second law of motion. That the same force for the same time causes the same change in momentum for the different bodies. In the preceding observations, the vector, here we learn all these things. Who can hurt his character? Now we learn this one, that is, in the preceding observation, the vector. Now this is in the preceding observations, the vector character of momentum has not been evident. In the example so far, momentum and change in momentum both have the same direction, but this is not always the case. Suppose a stone is rotated with uniform speed in a horizontal plane by means of a string. The magnitude of momentum is fixed, but its direction changes. A force is needed to cause this change in momentum vector. This force is provided by our hand through the string. Experience suggests that our hand needs to exert a greater force if the stone is rotated at a greater speed but in a circle of a smaller radius or both. This corresponds to greater acceleration or equivalently a greater rate of change in momentum vector. This suggests that the greater the rate of change in momentum vector, the greater is the force applied. Right? Now we learn that force is necessary for changing the direction of momentum, even if its magnitude is constant. We can feel this while rotating a stone in a horizontal circle with uniform speed by means of strain. These qualitative observations relate to the second law of motion expressed by Newton as follows. The rate of change in momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. Thus, if under the action of a force F for some for time interval del t, the velocity of a body of mass m changes from v to v plus del v, that is its initial momentum. And p equal to mv changes to del p, that is m into del v, according to second law. Every second law, F is directly proportional to del P by del T, or F is equal to K into del P by del T. Where K is the constant of proportionality. Taking the limit del to tends to 0, the term del T by del T becomes the derivative or differential coefficient of P with respect to T denoted by dP by dt. Thus, we can say F equal to K into dP by dt for a fixed body of fixed mass m, dP by dt equal to dt of mp m into dB, because m is constant, or m into a. And that is the second law can also be written as k F equal to k into m into a, which shows the force is proportional to the product of mass m and acceleration a. The unit of force has not been defined so far. In fact, we use equation 4.4 to define the unit of force. We therefore have the liberty to choose any constant value for k. For simplicity, choose k equal to 1. The second law then is F equal to dPdt or m into a. In SI unit, force is one that causes an acceleration of 1 meter per second square to a mass of 1 kg. The unit is known as Newton. 1 Newton equal to 1 kg meter per second square. Let us note at this stage some important points about the second law. In the second law, if F equal to 0 implies A equal to 0. The second law is obviously consistent with the first law. The second law of motion is a vector law. It is equivalent to three equations, one of each component of the vectors. The f is equal to dpx by dt, that is m a into x. F equal to dpy by dt m a y. Fz equal to dpz by dt m a z. This means that if a force is not parallel to the velocity of the body but makes some angle with it, it changes only the component velocity along the direction of force. The component of velocity normal to the force remains unchanged. For example, in the motion of a projectile under the vertical gravitational force, the horizontal component of velocity remains unchanged. The second law of motion given by equation 4.5. The second The second law of motion given by equation 4.5 is applicable to a single point particle. The force F in the law stands for the net external force on the particle and is stands for acceleration of the particle. It turns out, however, that the law in the same form applies to a rigid body, or even more generally to a system of particles. In that case, F refers to the total external force on the system and A refers to the acceleration of the system as a whole. More precisely, A is the acceleration of the center of mass of the system, about which we shall study in detail in chapter 6. Any internal forces in the system are not to be included in F. Acceleration at an instant is determined by the force at that instant. The moment after a stone is dropped out of an accelerated train, it has no horizontal acceleration or force. If the air resistance is neglected, the stone carries no memory of its acceleration with the train a moment ago. The second law of motion is a local relation, which means that the force F at a point in space, location of the particle at a certain instant of time, is related to A at that point at that instant. Acceleration is and here and now is determined by the force here and now, not by any history of the motion of the particle. Right? Now we learn this one, that is this question answer. There is a question here, a bullet of mass 0. We will learn later on the question answers. This is the question, this is the answer. There is another question. Now we will learn about impulse. We sometimes encounter examples where a large force acts for a very short duration, producing a finite change in momentum of the body. For example, when a body hits a wall and bounces back, the force on the body with the wall acts for a very short time when the two are in contact. Yet the force is large enough to reverse the momentum of the ball. Often in these situations, the force and the time duration are difficult to ascertain separately. However, the product of force and time, which is a change in momentum of the body, remains a measurable quantity. This product is called impulse. Impulse equal to force, time, duration, that is equal to change in momentum. A large force acting for a short time to produce a finite change in momentum is called an impulsive force. In the history of science, impulsive forces were put in a conceptually different category from ordinary forces. Newtonian mechanics has no such distinction. Impulsive force is like any other force except that it is large and acts for a short time. Here you see that a batsman hits back a ball straight in the direction of the bowler without changing its initial speed of 12 meters per second. If the mass of the ball is 0.15 kg, determine the impulse imparted to the ball. Assume linear motion of the ball. Hence, a change in momentum equal to this one, that is 3.6 Newton. In the direction from the batsman to the bowler, this is an example where the force on the ball by the batsman at the time of contact of the ball and the bat are difficult to know, but the impulse is readily calculated. Newton's third law of motion. The second law relates the external force on a body to its acceleration. What is the origin of the external force on the body? What agency provides external force? The simple answer is Newtonian mechanics is that the external force on a body always arises due to some other body. Consider a pair of bodies A and B. B gives rise to an external force on A. A natural question is, does A in turn give rise to an external force on B? In some examples, the answer seems clear. If you press a coiled spring, the spring is compressed by the force of your hand. The compressed spring in turn exerts a force on your hand and you can feel it. But if the bodies are not in contact, the part pulls a stone downward to its gravity. Does the stone exert a force on the earth? The answer is not obvious since we hardly see effect of the stone on the earth. The answer according to Newton's is yes. The stone does exert an equal and opposite force on the earth, but we do not notice it since the earth is a massive and the effect of a small force on the motion and the effect of a small force on its motion is negligible. Thus, according to Newtonian mechanics, force never always singly in nature. Force is the mutual interaction between two bodies. Forces always occurs in pairs. However, further, the mutual forces between two bodies are always equal and opposite. Further, the mutual forces between two bodies are always equal and opposite. This idea was expressed by Newton in the form of This idea was expressed by Newton in the form of the third law of motion. To every action, there is always an equal and opposite action. Newton wording of the third law is so crisp and beautiful that it has become a part of common language. For the same reason, perhaps misconceptions about the third law abound. Let us note some important points about the third law, particularly in regard to the usage of the terms action and reaction. The terms action and reaction in the third law mean nothing else but force. Using different terms for the same physical concept can sometimes be confusing. A simple and clear way of stating third law is as follows. Forces always occur in pairs. Force on a body A is by B is equal and opposite to the force on the body B by A. The term action and reaction in the third law may give a wrong impression that action comes before reaction. Action is the cause, reaction is the effect. There is no cause effect relation implied in the third law. The force on A by B and the force on B by A act at the same instant. For the same reasoning, any one of them may be called action and the other reaction. Action and reaction forces act on different bodies, not on the same body. Consider a pair of bodies A and B. According to third law, if force on A by B is equal to minus force on B by A. Thus, if we are considering the motion of any one body A or B, only one of the two forces is relevant. It is an error to adapt the two forces and claim that the net force is zero. However, if you are considering the system of two bodies as a whole, F of AB and F of BA are internal forces of the system A plus B. They adapt to give a null force system. Internal forces in a body or a system of particles thus cancel away in pairs. This is an important fact that enables the second law to be applicable to a body or system of particles. Here is an example of this one. Two identical billiard balls strike a rigid wall with the same speed but at a different angles and get reflected without any change in speed. As example 4.6. What is the direction of the force on the wall due to each ball? The ratio of the magnitude and magnitudes of impulses imparted to the balls by the wall. Here you see the answer is an instinctive answer to one might be that the force on the wall is in case A is normal to the wall, while in case B it is inclined at 30 to the normal. The answer is wrong. The force on the wall is normal to the wall in both the cases. How to find the force on the ball? The trick is to consider the force, the impulse on the ball due to the wall using the second law, and then is the third law to answer 1. Let you the speed of each ball before and after collision with the wall and m be the mass of each ball. Choose the x and y axis as shown in the figure and consider the change in momentum of the ball in each case. Case A. Initial momentum equal to m into u and Py initial 0, Px final minus mu, Py final 0. Impulse is the change in momentum vector. Therefore, x component of impulse equal to minus 2 mu and y component of impulse equal to 0. Impulse and force are in opposite direction. Clearly, from above, the force on the ball due to the wall is normal to the wall along the negative x direction. Newton's third law. The force on the wall due to the ball is normal to the wall along the positive x direction. The magnitude of force cannot be ascertained since the small time taken for the collision has not been specified in the problem. In case B, Px initial that is a mu cos 30 Px and Py is minus mu sin 30, right? And Px final minus mu cos 30 minus mu cos 30 and Py minus mu sin 30, right? One note, Px changes sign after collision, Py does not. Therefore, S component of impulse equal to minus 2 mu cos 30 and Y component of impulse is equal to 0, right? The direction of impulse and force is the same as in case in A and is normal to the wall along the negative x direction. As before, using Newton's third law, the force on the wall due to the wall is normal to the wall along the positive x direction. The magnitude of the ratio of the magnitudes of the impulses imparted to the ball in A and B is 2 mu by 2 mu cos theta. That is 2 by root 3, that is 1.2. Now we'll learn about conservation of momentum, right? What is that? Conservation of momentum. Now we learned about conservation of momentum. The second and third law of motion leads to an important consequence, the law of conservation of momentum. Take a familiar example. A bullet is fired from a gun. If the force on the bullet by the gun is F, the force on the gun by the bullet is minus F according to the third law. The two forces act for a common interval of time del t according to the law. According to the second law, F del t is the change in momentum of the bullet and a minus f del t is the change in momentum of the gun. Since initially both are rest, the change in momentum equals the final momentum for each. Thus if Pb is the momentum of the bullet after firing and Pg is the recoil momentum of the gun, Pg equal to minus Pb, that is Pb plus Pg equal to 0, the total momentum of the bullet and gun system is conserved. Thus, an isolated system, a system with no external force, mutual forces between pairs of particles in the system can cause momentum change in individual particles. But since the mutual forces for each other, each pair are equal and opposite, the momentum changes cancel in pairs and the total momentum remains unchanged. This fact is known as the law of conservation of momentum. The total momentum of an isolated system of interacting particles is conserved. An important example of the application of law of conservation of momentum is the collision of two bodies. Consider two bodies A and B with initial momentum PA and PB. The bodies collide, get apart, with final momentum PA' and PB' respectively by the second law. F of F AB del T, a P A dash minus PA, and FBA, that is PB dash minus PB, where we have taken a common interval of time for both forces, that is the time for which the two bodies are in contact. Since f of A equal to minus f of BA by third law, P A dash minus PA equal to P minus PB dash minus PB. Therefore, P dash, that is this shows that the total momentum, that the final momentum of the natural system equals its initial momentum. Thus, you notice this is true whether the collision is elastic or inelastic. In elastic collision, that is the second condition, that the total initial kinetic energy of the system equals the total final kinetic energy. In elastic collision, equilibrium of a particle. How to find the equilibrium of a particle, right? Equilibrium of a particle in mechanics refers to the situation when the net external force on the particle is zero. According to the first law, this means that the particle is either at rest or in uniform motion. If the two forces F1 and F2 act on a particle, equilibrium requires F1 equal to minus F2, and the two forces on the particle must be equal and opposite. Equilibrium under three concurrent forces F1, F2, and F3 requires that the vector sum of the three forces is zero, that F1 plus F2 plus F3 equal to 0. In other words, the resultant of any two forces, say F1 and F2, obtained by the parallelogram law of forces must be equal and opposite to the third force F3. As seen in figure 4.7, the three forces in equilibrium can be represented by the side of a triangle with the vector arrows taken in the same sense. The result can be generalized to any number of forces. A particle is in equilibrium under the action of forces F1, F2, Fn if they can be represented by the sides of a closed n-sided polygon with arrows directed in the same direction. Equation 4.11 implies that f1x a plus f2x plus f3x equal to 0, f1y plus f2y plus f3y equal to 0, f1z plus f2z plus f3z equal to 0, where fx, fy, fz are the components of f1 along x, y, and z direction separately. Now we'll learn how the examples of this one we'll do it later on, and now we'll find the consider there is a solution, and we'll learn about common forces in mechanics. That I'm going to learn this one, right? Common forces in mechanics. In mechanics, we encounter several kinds of forces. The gravitational force is of course pervasive. Every object on the earth experiences the force of gravity due to the earth. Gravity also governs the motion of celestial bodies. The gravitational force can act at a distance without the need of any intervening medium. All the other forces common in mechanics are contact forces. As the name suggests, a contact force on an object arises due to contact with some other object, solid or fluid. When the bodies are in contact, a book resting on a table is a system of rigid bodies connected by rods, hinges, and other types of supports. There are mutual contact forces for each pair of bodies satisfying the third law. The component of contact force normal to the surface in contact is called normal reaction. The component parallel to the surfaces in contact is called friction. Contact forces arise also when solids are in contact with fluids. For example, for a solid immersed in a fluid, there is an upward buoyant force equal to the weight of the fluid displaced. The viscous force, air resistance, etc. are also examples of contact forces. Two other Two other common forces are tension in a spring and the force due to spring. When a spring is compressed or extended by an external force, a restoring force is generated. This force is usually proportional to the compression or elongation. The spring F is written as F equal to minus kx, where x is the displacement and k is the force constant. The negative sign denotes that the force is opposite to the displacement from the unstressed state. For an inextensive string, the force constant is very high. The restoring force in a string is called tension. It is customary to use a constant tension T throughout the string. This assumption is true for a string of negligible mass. We learned that there are four fundamental forces in nature. Of these, the weak and strong forces appear in domains that do not concern us here. Only the gravitational and electrical forces are relevant in the context of mechanics. The different contact forces of mechanics mentioned above fundamentally arise from electrical forces. This may seem surprising since we are talking of uncharged and non-magnetic bodies in mechanics. At the microscopic level, all bodies are made of charged constituents, nuclei, electrons, and the various contact forces arising due to elasticity of bodies, molecular collisions and impacts, etc., can ultimately be traced to the electrical forces between the charged constituents of bodies of different bodies. The detailed microscopic origin of these forces is, however, complex and not useful for handling problems in mechanics at the macroscopic scale. This is why they are related as different types of forces with their characteristics properties determined empirically. In the next video, we'll learn about friction. Dear friends, if you like this video, please subscribe, like, and share. Thank you. Thank you everybody for watching this video.